The following is a conversation with Captain Peter Turner. Peter is a veteran aviator, a man who has spent thousands of hours in the cockpit and a decade in the data logs of Malaysia Airlines Flight 370. While much of the public disclosure focuses on the why, the human drama, and the psychology of intent, Peter focuses on the how. He looks at the aircraft as a mechanical organism, a complex web of electrical buses, satellite data units, and emergency logic. As the Ocean Infinity 2026 search enters its final stages, the pressure to find answers has never been higher. To Peter, the mystery isn't just about a point on a map. It's a technical puzzle that challenges our understanding of modern aviation safety. He presents a compelling systems-first model of a cascading failure, a narrative not of a crime, but of a machine and a crew fighting a silent, high-altitude battle. I have often thought that technology is a fragile layer between us and the vast, indifferent nature of the ocean. When that layer fails, we are left with nothing but data pings and silence. Peter attempts to translate that silence into the language of engineering. To help you follow along, we jump right into the heart of the data, referencing the technical documents we have compiled given to us by Peter, starting with a look at the satellite logon event at 1825 UTC. This is the Sit Down with Sid podcast, and now here is my conversation with Captain Peter Turner. Good morning, good afternoon, and good evening to our audience from around the globe. I'm your host, Sid, and welcome back to the Sit Down with Sid podcast, where we bring people together one conversation at a time. A quick note before we begin. MH370 remains a complex mystery. The views expressed here are those of our guests, as we provide a platform for various perspectives in this ongoing story. Joining us today is a man who brings a lifetime of technical expertise to this puzzle, Captain Peter Turner, a veteran pilot who understands the language of an aircraft better than most. While many look at the maps, Peter focuses on the mechanics and flight paths from the perspective of the flight deck. Peter, as we sit here today in the final weeks of the Ocean Infinity 2026 search, your insights into the how and where of this flight is more critical than ever. It is a privilege to have you here. Welcome to the show.
Thank you, Sid. Thanks for having me on. Namaste. And hopefully we'll just go through the evidence. And I don't have the definitive answer because we haven't found the aircraft yet. But hopefully, just looking at the evidence, the next hour or so we'll look at the evidence and hopefully come to the most likely conclusion and why Ocean Infinity has still yet to find the machine.
Perfect. So, Captain Peter, after reviewing the technical document that you shared with us, to ensure our audience can follow the complexities of your mechanical failure theory, we have carefully dissected each page of the documentation for question. So, if you're ready, I am ready, and let's get into it.
Go ahead.
Our first question. So, I would like to share my screen with the audience as well here. So, let me just share this screen. Okay. Okay. All right. Much of the public disclosure centers on the idea of deliberate human intervention. Peter, we are looking at this page of your technical breakdown where you have circled a specific event at 1825:27, the satellite logon. From your perspective in the captain's seat, what are the technical red flags like this reboot that suggest we should be looking at a systems failure instead of a manual one?
Okay, so what you have there is that's a printout that I actually made. So that's not actually a Malaysian official document there. So that was my prediction on where the aircraft went. So this is an hour after the disappearance. So you've got there 18:25 and 27 seconds. So that's the time in UTC. And that's where
Mhm.
the aircraft I predicted would be at that particular time. So the interesting thing about that is you can see those two vertical red lines there. They're sort of like both arc ones, if you're familiar with that. That's the distance the aircraft was predicted to be from the satellite at that particular time. So you can work out how long it takes for the communication signal to get to the satellite. So by using the speed of light, you can work out how far the aircraft is from the satellite. So that's how you get the arcs. So there's arc 1 through to arc 7. But what's unique about this one is that when the aircraft logged back on 1 hour after it disappeared, the
Mhm.
actual flight ID, MAS370, was missing, but the aircraft ID was still there. So when the aircraft communicates with the satellite, it will send its registration, and also after the crew have put in the flight number, the flight ID is sent as well. But this is strange because the flight ID was missing. Now, if someone had just simply manually deleted the flight ID, then that would
Mhm.
cause a log off, which was never received by Inmarsat. So no one simply manually deleted the flight ID. You would have to go through an extreme complex procedure and scenarios to try and delete the flight ID without sending a log off. However, that doesn't still hide your identity because
Mhm.
the aircraft registration is still there. So that's strange in itself. So why are you going to all this point to try and hide your flight ID but still leave your aircraft ID? Seems a bit strange. What the simplest answer would have been just to leave the satellite system off altogether. Therefore, there would be no reboot. So because someone's rebooted the system, the aircraft is then logged back on. So the reboot itself showed that there was the frequency offset with that frequency transfer was a consistent with a startup signature. So in other words, the satellite data unit or the satellite communications had been depowered for 22 minutes. Now the satellite data unit, or the SDU, is powered by the left main AC bus, which is like a power supply bus which powers that satellite data unit. So someone after 22 minutes has repowered that bus, and that has caused the log on. And the lack of flight ID is probably more consistent with the crew restarting the systems, trying to get systems back up online, rather than someone manually deleting the flight ID. But the biggest one, while we're looking at it's more of a technical problem, is back at the transponder. Because when the left transponder back over at Agari, when it started to fail or cease
Mhm.
transmission, it briefly transmitted zero. So zero means the aircraft is on ground. So when we did in-flight testing of just turning the transponder off in flight, we couldn't actually replicate a zero indication on the ground radar. So that's the blips on the radar screen. We even tried with altitude reporting off. So there was no way we could actually replicate the failure that was observed on the radar system that controllers see by just someone manually switching off the transponder panel. So if that's not possible from the cockpit, so any scenario that relies on someone turning off the transponder, whether it's through altitude reporting off from the cockpit, it just doesn't meet the evidence. So therefore, you're looking at a technical issue. So the
Mhm.
transponder wasn't turned off; it just ceased transmitting due to a technical failure, and that's contrary to what the Malaysian governments have told us. They said the transponder was switched off, but in-flight testing just doesn't agree with that.
Wow, that's mind-boggling because from, as you said, from what I've also heard is that the transponder was switched off and then it came back on. But according to you, that is not possible.
The transponder, no. The transponder ceased transmitting. That was it. End of story.
Oh, wow. Okay, perfect. So I would like to show the other clip that you sent us, and let me share the question. Let me share the screen, and I'm going to ask you this question as well. Okay, here we go. Okay, now. When the transponder and communications went silent, many assumed foul play. On this page, we see the investigation exit and investigation entry points at the boundary of Malaysian and Vietnamese airspace. What specific emergency protocols would a crew be prioritizing in a zone like this that might look like going dark to a layperson?
Okay, so what you're seeing there is a bit of my from my presentation as well that I've done around the countryside here. And if you've seen my presentations, you may have seen my hypothesis was that Malaysia Airlines serviced the crew oxygen bottle, and it was the oxygen bottle that actually ruptured in flight was the root cause of the issue. So you've got to remember that Malaysia Airlines serviced the crew oxygen bottle shortly before departure. So these bottles are located in the electronics bay, which is under the floor of the cabin there towards the front. Now these bottles sit in the middle and slightly to the left in the electronics bay, and there's two bottles. They're about 3,150 litres each, and they've been repressurized.
Oh,
So
wow.
they're very large. They're very large. So hypothetically, so from all my investigations, hypothetically, if we say that the Malaysians serviced these bottles incorrectly, so hypothetically, let's say they used household soap and water rather than leak detector fluids test to see for oxygen leaks. So after you've repressurized them, you then have to spray on, you're supposed to spray on leak detector fluid to see that there's no leaks from that valve in that bottle. But if they're using household soap and water, which is cheaper, that can cause some problems because the water in tap water contains chlorine and fluoride, which is good for killing bacteria in your tap water, but it's not very good for stainless steel because chlorine and fluoride will actually corrode stainless steel. So if you're doing this for 12 years, that's going to corrode that valve. Now, if you then do that procedure and then repressurize the bottle has just been repressurized from 1,120 psi up to 1,800 psi, then the pressure on that valve and the wall of the cylinder has actually increased. Now, as the aircraft climbed to altitude, the cabin altitude pressure has reduced as the cabin altitude climbed up as it normally does. So the cabin pressure has actually slightly reduced. So again, there's more pressure on that cylinder. And then as you can see here, as the aircraft goes to Agari, the aircraft was cleared to go from Agari to Bitod. So there's a slight right turn there, and that would increase the G loading, and that's probably just the last straw that broke the camel's back. And then that last little bit of G loading, after all that pressure has then gone boom. Now, once it's gone boom, the crew are going to be overwhelmed by failures because that oxygen bottle is in the electronics bay next to the left brain of the aircraft. So the crew are going to be startled by all the failures they're going to get. And what you're going to see is you're going to see the transponders going to go out. You're going to see also there's not going to be any radio calls because the AM unit or the audio management unit doesn't work. The crew are just going to be overwhelmed by failures and failures and failures. And what are they going to do? They're going to do aviate. So first of all, they're going to fly the plane, regain control of the aircraft. Then they're going to navigate. So where's the nearest airport? With all these failures, you're not going on to Beijing. So the nearest airport is over your left shoulder, which is Kotobaro. Hence, the aircraft turned back towards the left, towards the nearest suitable airport. And communicate, well, that's not possible if there's no radios. So the only option is to turn on a mobile phone. So as far as you can see here, yeah, for someone on the ground, you'd see the aircraft go dark. So no transponder, no radio calls, and you'll see it turning back towards the nearest airport.
Wow. Okay. Let's. I do have a lot of follow-up questions, which I will definitely ask as we go along. Let me share our other screen. I want to thank the audience, first of all, for their patience because this is extremely technical and it took us 2 hours to completely understand for ourselves as well. Okay. Now, all right. So you have focused heavily on the electronics bay beneath the cockpit. On this page, you have highlighted the N571 airway and its proximity to Banda Aceh. Can
Yeah.
you explain why a fire or decompression in that specific nerve center is more likely than a cockpit-centered emergency?
Well, when you look at all the observed failures and from my analysis, other failures from that oxygen bottle rupture, then everything that failed ele
Mhm.
electronically relies on those equipment directly or indirectly next to the oxygen bottle. So that's all your transponders, uh, communications, etc. But if that's gone, you're going to have all these other failures as well. You're going to have screens fail. You're going to have flight control issues because it's the left electronic brain we're talking about here. You're going to have auto throttle is going to fail. You're going to have pressurization system fail. It's just a Swiss cheese model. So the aircraft was repressurized, it's climbed altitude, gone the altitude, and gone to the turn, and then gone boom. A simple single point failure of the oxygen bottle just going boom in the electronics bay is more plausible than someone turning off this switch, turning off that switch, turning off this switch, turning off this switch, turning off that switch in the cockpit rather than just a single point of failure. So when you look at it, it looks like that the aircraft has turned back towards the nearest airport. So that's Cotabaru. So fire, yes, I don't predict that it's a fire, because if there was a fire in the electronics bay or anywhere in particular, the aircraft would not fly for the 7 hours. By contrast, if you go with the rupture of the crew oxygen bottle in the electronics bay, well, the crew are going to be overwhelmed by failures, as I said before, but that's going to set up, if the fuselage is still intact because the bottle's in the middle of the electronics bay, then the pressurization control has failed and the bleed air system has failed. So the aircraft's going to slowly, gradually decompress. So if there's a gradual decompression happening, it's going to be very hard for the crew to detect that because it's very insidious. It happens so slowly you can't detect it physically. Contrast that to Qantas QF30, which had an oxygen bottle rupture as well, but that oxygen bottle was on a 747 and it was situated on the fuselage skin. So in that scenario, they'd climbed altitude as well, and during cruise, that oxygen bottle ruptured. Now that blew a 2 meter hole in the side of the fuselage. Now once you've done that, you've got an explosive decompression, and that's easy to detect physically. You just go, whoa, there's an explosive decompression, quick, get your oxygen mask on, down you go. Whereas with MH370, if it's a gradual decompression, then yeah, it's going to be hard to detect physically, and you may actually be so focused on dealing with all the emergency problems and all the checklists that after 20 or 30 minutes before the cabin altitude has risen to a dangerous level of cabin altitudes, that hypoxia may have already set in. So hypoxia is a lack of oxygen. So if someone has faced with hypoxia, like the crew possibly have after 20, 30 minutes as the cabin altitude is rising, they're going to have tunnel vision, they're going to have reduced night vision, they're going to have impaired judgment, they're going to be mentally confused, because once the brain is starved of oxygen, you start making silly decisions, and you might even recognize something, but you don't have the mental capacity to then correct that scenario. So that'll keep going on worse and worse. So they'll get euphoric, they'll get cyanosis, they'll totally lose situational awareness, and they'll start making stupid decisions. So you can see that in this scenario, if someone for some reason has programmed a diversion to Banda Aceh, which seems a bit strange, but not to
Hmm.
someone who's suffering from hypoxia. Now, if you're programming this route and then you should pass out from hypoxia, the aircraft will just follow this route and then will continue on autopilot and keep going south for another 7 hours until fuel exhaustion.
So it can still fly for 7 hours, even with this decompression, which is not physically visible.
Correct. Yeah, the aircraft systems don't require pressurization system. The electronics don't require that. So if someone's programmed a diversion to Banda Aceh and the autopilot's back on, the aircraft will just follow that route and away it goes for 7 hours, even if everyone has passed out from hypoxia.
Oh, wow. Okay. It keeps getting very interesting. Thank you for your sharing your
Mm.
insights. Let me share this. Okay. Now, in this, I'm sharing the screen one more time. My follow-up question is, what is the significance of the left wire integration panel? Referring back to this page, as I said, we see the last primary radar contact at 18:22 and 12 seconds UTC. How could a failure in this specific area explain why the plane remained airworthy but became effectively invisible to radar just moments before their satellite reboot?
Okay, so it's getting very technical, but obviously a lot of people don't have access to the 777 manuals, but the Boeing 777, to save costs rather than having wires go everywhere, they'll have like two electronic brains. So all and for redundancy, they'll have like left systems and right systems rather than just having one system. They'll have like a left something and they'll back it up with a right something system. So primarily you'll see that the left brain will control all those left systems and the right brain will control all the right systems. And some systems are so important, they're actually controlled by left and right brains for redundancy. So when you just look at all the failures, so left transponder had failed. Remember, the left main AC bus had been repowered. My analysis looking at the left flight management computer, the left auto throttle, left high gain antenna, everything is left. So even the AMU is a left system as well. So that's all comes into the left brain. Now, just below the oxygen bottle is the left wire integration panel, which is a critical junction for all the left systems going into the left brain. So if the oxygen bottle has ruptured, it's going to cause extensive damage to the immediate area. And that would include the left wire integration panel. So as soon as that's gone, the crew are going to have failures. Now that panel has hundreds and hundreds of wires going into it. It's not just one or two. It has hundreds of wires, and once that's gone, it's going to be a really complex problem for any crew to face. Now, will the aircraft still fly? Yes, because of redundancy. So you've still got all the right systems, which is away from the oxygen bottle. So you've still got flight controls being fed, powered by the right system. You've still got other things coming from the right system. However, what you've got is you've got a crew facing cognitive overload from so many failures. And they could have had 6 display screens, now condensed down to 2. So the situational awareness is just so complex that I can see it's very easy that if you're so focused on this complex problem that you're going to miss the hypoxic event that's happening, and eventually you're going to pass out. So regarding the radar, though, people say the transponder was turned off. Well, no, in-flight testing doesn't show that, and people say that the aircraft was invisible. Well, that's not actually totally true either, because yes, it's the transponder is putting a blip on the radar screen, on the air traffic control's radar screen. It's now not visible to them. However, there is still primary radar systems, and all pilots know about primary radar system. So it's actually good way back at Agari, when the aircraft turned back, it actually flew into range, and as it goes up the Malacca Strait, a total of 10 primary radar sites. So you've got primary radar sites on, I think there's about 5 in Malaysia that would have seen it. So there's one at Kong Kadak to the south of Kota Bharu. You've got one at Kota Bharu. You've got Langkawi, you've got Butterworth and Penang. So there's 5 there, which would have is now actually flown into the range of. And then there's 2 in Thailand. So you've got Hat Yai and Phuket. And then you've got another 3 over in Indonesia. So Lok Sumawi, which is on the northern coast of Sumatra, Sabang, which is on the northern tip of Sumatra over near Banda Aceh, and Sabolga on the west coast. So as far as going invisible, no, the aircraft actually turned back into range of 10 primary radar sites. If it was wanting to disappear, it should have continued east away from primary radar. Then you would be outside the range of the primary radar. And if you were really clever, you would have actually waited until north of Vietnamese airspace, where there is no primary, there's a little black hole where there's no primary radar range. You could have turned east there and went over to the Marianas Trench. But back to MH370, it's actually turned back in towards a range of 10 primary radar sites. Now, what you see on this picture here is you can see the last primary radar point at 18:22 and 12 seconds. So that's the last primary radar point from Malaysia. So that's the last Malaysian point. So this is out in the Malacca Straits. That's over 300 nautical miles away from Malaysia. at that point there is three other primary radars which would have easily have captured MH370. So you
Hmm.
would easily see where the aircraft went after this last primary radar point. So that would be the Thai radar at Phuket. If data was available from that, you would see where MH370 went, and the two Indonesian ones. So if you saw the radar data from Lok Sumawi and from Sabang, you would definitely see where MH370 went, and it would have narrowed down the search area. So my prediction, and looking at the data, the aircraft flew right over the top of Banda Aceh, which is straight past Sabang's radar. So it should have picked it up. And if you had that early on, you would have narrowed down the search and you would have found MH370 a lot sooner.
But did those radars pick MH370 up? That's my question. You mentioned 10 primary radars over three different airspace.
Correct. Well, if Malaysia has picked up the this last primary radar point at 18:22 and 12 seconds,
Hmm.
then that point is definitely within range of the other three. So Lok Samawi, Sabang, and Phuket. But the official response is that data is not available.
Hmm. Wow, interesting. Okay, let's move on to the next one. And Captain Peter, if you think so, once again, we try to make it as simple as possible for people to understand. So if you think at any point my wording is too complicated, too technical, please correct it for us.
Yeah.
You being the expert. So okay, perfect. Let's see the next one. Let me share the screen, and then I am going to ask you the follow-up question. Okay, here we go. Okay. Uh, Now we have discussed the sophisticated spoofing and the active pilot control thesis on this show before. Looking at this, your predicted endpoint sits at 34.25 south, 93.25 east. If a mechanical failure occurred as you suggest, how do you explain the specific flight path changes and the physical debris found by Blaine Gibson that some say points to a high speed impact?
Yeah, well, when you run out of fuel, the aircraft will go out of control and will go into a high speed, out of control dive. So it does match with what Blaine's Gibson has found. Yeah, he's amazing gentleman, Mr. Gibson, finding all that debris. And without him, MH370 would, you know, we wouldn't have all this debris that we found. I think it's over 33 or maybe unconfirmed 60 odd. But so, yeah, thank you to Mr. Blaine Gibson for all his work he's done. Some other people have predicted flight paths down here.
Hmm.
Uh, More of the active pilot route and then gliding. So you would have seen Ocean Infinity had searched outside the arc, so further to the southeast. So you can see this picture here. This is one of my pictures, which I've used some other people's group. You can see the data. You can see Independence Group's hotspot there on that little purple line. So that's
Okay.
their that's the seventh arc, that little purple line, and you can see
Hmm.
up towards the left top corner. You can see the sixth arc coming in there, sort of like that light blue indigo line,
Right, right.
and that's my hotspot there, little spot, and because of inaccuracies, I assume 25-mile radius, but I have got a broader area as well, and then you have the Jean-Luc Marchand and Captain Blelly. They're down towards the southeast of this search area, which has been searched by Ocean Infinity to no success. But I should mention, I should apologise to Jean-Luc Marchand. I think in my talks at the Airways Museum at Essendon Airport and in Perth and at the Peninsula Aero Club in Tyabb, southeast of Melbourne, I think I referred to him as a French national, but he's actually Belgian, so I do apologise for that. And my interaction with Captain Blelly, he's been very professional. So yeah, we have differing theories, but
Hmm.
his their area has been searched. But mine is basically simple. Mine's you won't find a simpler flight path. Divert to Banda Aceh with left systems fail and just let it go. Whereas if you look at all the others, they are turn left, turn right, descend, climb, speed. And it just has more assumptions, more assumptions, more assumptions. And when you start descending and climbing and turning and all that, the fuel flows just go through the roof. And from my analysis, the only way you can get to this spot is I'll show you later is I could probably talk about it now if you want, is that the only way you can get there is at a reduced speed with the bleed air system inoperative, which would lead to hypoxia. So if you want, I could. Yeah, well, I think I need another picture though to show you
Sure.
back.
So I
Yeah,
have another 5, 6 questions with the different slides that you shared. So
yeah.
uh, maybe if I continue with my sequence, you can probably pinpoint this is the one you wanted to talk about, if
Okay,
that's okay.
so I don't think I answered your question there. So once you run out of fuel, yes, the aircraft will go into a dive, and yes, you'd go into a high-speed descent. So that's consistent with the satellite data and consistent with all the debris that Blaine Gibson have found, and consistent with the ATSB, because the ATSB had found the right flapper on and the right outboard flap.
Hmm.
Um, they had to be in the retracted position because if they were down for ditching, the point of impact between those two adjacent control surfaces wouldn't match. So therefore, the ATSB found from the physical evidence that the flapper on and the flap were in the retracted position. So the aircraft wasn't glided or ditched. It basically ran out of fuel and went into a high-speed dive. Another point is people talk about the Roy debris. That's
Hmm.
the Rolls-Royce on the edge of the engine cowl. So if the aircraft has run out of fuel and gone to a high-speed dive, like the BFO is predicting 15,000 feet per minute descent rate,
Wow.
then that aircraft is going down extremely rapidly. There's going to be shock waves. If it's going nearly close to the speed of sound, there'll be shock waves formed around that engine cowl. And once there's a shock wave formed around it, that's probably why the Roy piece has been ripped off during a high-speed descent. Now, if that's ripped off, then that's why the Roy has probably detached from a different location to where the rest of the debris is. Hence, that's why the Roy debris ended up
Mhm.
further west in the debris analysis.
Huh. Okay. So my next 2 questions, I have the same slide, so I'm going to keep it up and I'm going to
Yeah.
ask you 2 follow-up questions on those. So let me just share the slide first with you. Here it is. And okay, my first follow-up question to this one is the sharp turn back toward the Malay Peninsula is often cited as a proof of a rogue pilot. However, looking at the technical data on this page, you show a remarkably stable ground speed of 504.4 knots during that maneuver. In your mechanical failure model, how does that turn happen? Is it a manual move or a programmed emergency return?
Okay, it's probably better if you go back to the primary radar
Previous?
one with the turn back with the entry and exit. I'll start there and try and explain it to you, and then we'll go
Sure.
to that chart.
Sure.
So,
One sec. Let me open that slide and
sorry for this,
so
Sid.
no. Please listen.
Yeah,
As I said, this took us few hours to even
yeah,
understand. We wanted to make sure that we know what we are talking about and we
yeah.
asked you the right questions since you are the expert. So you want us to open the investigation exit and entry points
Yeah, that one.
okay, sure. Let's do this. I found it. Right, here we go. Okay, here we go. So perfect. Here we go.
Okay, so we'll go back and talk about this primary radar, this sharp turn back. So you can see here on this is again my chart with the primary radar data underlaid there, which the primary radar data is that white, really noisy, faint line you can see underneath. So that little faint white line goes underneath, goes through a gari, turns right towards Bidon. You can see it goes pretty straight. And then
Mhm.
just there, yep, the aircraft
Okay.
then turns almost at 90 degrees or a little bit more than 90 degrees on the spot to the left, that little white
Hmm.
line.
Hmm.
But what you're looking at here is filtered primary radar. So this is the filtered primary radar from the Malaysian military. So what you're not seeing is raw primary radar. So raw primary radar is basically like X marks the spot. So this is not what you're seeing. That's the raw primary radar has never been released by Malaysia. So what you're seeing here is the filtered primary radar. So filtered primary radar basically has a tracking algorithm like a Kalman filter, which will take all those raw points and then smooth it out into a smooth, continuous white line. But it's still noisy signature, so you can see why this white line it's still a bit fuzzy. Now,
Yes.
what it is though is when you've now got filtered primary radar, it now introduces its own errors. So people have said that the aircraft turned at the impossible 90 degrees on the spot, but no, this is known errors with filtered radar. So what you've got there, you got down there at Agari, as the aircraft's going up towards Agari. So if you were sitting at Penang, next to the radar site, the primary radar site, and looking at MH370, you would see a side profile. I'm not sure whether you can see that, but you'd see a side profile of the aircraft. So that would be a good, what they call a radar cross section. So they get good returns. So as the aircraft's going up towards Agari, it's seeing the side. Now, as the aircraft turned at Agari, remember it was cleared to go from Agari to Bitod, the ADS-B data showed that it turned prior to Agari to go to Bitod as it was cleared. But you can see that the filtered primary radar, it just, first of all, what it does, it says, oh, that could just be a noisy return. So it doesn't start the turn straight away. It just says it waits for a couple more sweeps of the radar. And then once there's more sweeps of the aircraft turning towards Agari, it then says, oh, okay, you have actually turned track, and then it'll catch up. So that's why you can see the filtered radar path goes through Agari before it turns to the right. So it's just predicting on where the aircraft is. Now, this is where it goes a little bit more. So it's predicting to go through Agari, which is not true. That's just because of the filtered radar computation is delayed in catching up. But as soon as the aircraft has now turned towards Bitod, it's now flying directly away from the satellite, from the primary radar site. So now the primary radar sites at Penang are only seeing the tail view of MH370. In other words, that's a very small radar cross section, and it will probably actually it won't pick up the target at all because this is at maximum range. So rather than dropping the signal altogether, the system, filtered radar, will coast the signal. So that's why you can see there's like an almost perfect straight line towards Bitod. So this is the radar just predicting, oh, well, I've lost where it is because it's lost a paint or a return of it. So it just predicts it for another couple of sweeps. Could be five sweeps. That could be another 50 seconds of just predicting going it straight to Bitod. Now, in the interim, so as it's predicting going towards Bitod, as the aircraft turns back towards the left, towards the nearest airport, it's going to again just bank back to the left. You're going to see a side profile. It's going to pick it up again. So during that mid-turn coming back, the radar will pick it up again. So the aircraft is now mid-turn, that orange prediction line, whereas the filtered radar has predicted it's still going to Bitod. So now that it's reacquired the target, how's it going to fix the picture? It's going to have to just draw a 90-degree turn to go catch up with the true position of the aircraft. Hence, hopefully I explained it, hence this filtered primary radar has got the error there. There's not the aircraft actually doing a 90-degree turn on the spot. It's just the filtered radar catching up with the raw primary radar data. Now the thing here is if you had the raw primary radar data, you could then plot it back in and you would see that the aircraft would probably just follow that orange line. So I've drawn in that orange line there. That's just a standard 25-degree angle of bank turn. So if you look at the turn diameter on the turn back towards Agari, that turn diameter, and we know the speed it was at Agari, it's just 25 degrees angle of bank. So it's nothing excessive at all. It's actually a standard maneuver that you could do. However, I'll point the last 2 points, is the investigation there. You can see the entry and exit points they used. They used the filtered radar as the entry and exit points. That's not going to work because you're using filtered radar, which has its own errors, and that's not the true position of the aircraft on those white lines. They're only just best guess due to the Kalman filter. And the last one is this turnback cannot be done in lateral navigation. So in other words, it's not in its normal natural navigation mode. This can only be done manually at 25-degree angle of bank. That's highly possible and probably what you would do. Or it's done in heading mode on autopilot with the bank selector at 25. So when they say the turnback was excessive, it's most likely just a standard 25-degree left turn towards the nearest airport.
Hmm.
Now we'll move back to the other one. The
Okay.
other,
Uh, may I ask you one thing? Because I remember when we spoke with Jean-Luc Marchand, he said that it was a sharp banking angle at 35 degrees and an autopilot restricts the plane at 25 degrees. Correct us if we are wrong here.
correct. So what he's doing there is you'll see the turn back in when it's heading back
Hmm.
towards the nearest airport. That little line there you can see is dead straight. uh,
Yeah,
near
right
the
here.
exit point there. Yeah, again,
Yeah.
because you're now looking head on at the aircraft, it's lost it's lost the target, so it's again coasting. It's just prediction. So
Hmm.
it's just predicting it there. So and by the time it catches up, it then has to widen out. So if you're following that white line, that's
Hmm.
not the true position. So I can see why he said 35 degrees, because he's trying to follow that white line. But the white line is just a best estimate and not a true position of the aircraft.
Wow. Okay. Let me go back to the previous slide and 1 second. This keeps on getting interesting and interesting. Uh, okay. So here we are. Now, I had two questions on this. My first question was uh, the ground speed, 504.4 knots. Uh,
Yep.
my question was, how does that turn happen at that speed? And is it a manual move or a programmed emergency return?
Okay. There should be another slide, I think. If you go, there's a slide of showing the turn back from Agari first before you get to this one. So if you just go to that one, Sid, I'll pick it up there for you.
Sure, 1 second. So altogether, we had 7 pages
Yeah.
and we dissected. Let me see. Do you recall the page number? If not, I'm
Oh,
going to open.
it's the one next
Because
to that one. So it would have been the one previous to it, what you just did, I think.
so if this is page, so this is page 7. So you're saying page 6.
Possibly, yeah.
Page 6 is actually the Ocean Infinity Search proposal.
Oh, okay. Must be two or three.
Okay, let me. 3 is the one that we showed you with the N571
Yeah.
airway. And let me just actually open the master file, and then you can actually guide us through that. 1 second, bear with us. Okay, here we go. Uh, okay, I have it right here, and you can. Sorry, bear with me. Here we go. Untitled. Yeah, share. Okay, so this is the master file, so I can just leave this one open, and I'll just ask the question from this.
Right, yeah.
Uh, okay, let me
Yeah.
know which.
That one. Yeah, that one.
Okay, okay, so
And
this
then,
one was my follow-up question. No problem. Go for it.
yeah.
Yes, go ahead.
Yeah, so go back to the previous slide.
Okay,
That slide, yep.
okay.
So what was your question again?
So this one, on this specific one was the sharp turn towards the Malay Peninsula is often cited as a proof of rogue pilot. You see a remarkable stable. Actually, this one is 505.3.
Yep.
This one, okay. On this specific page, we have this question. If the crew were incapacitated shortly after the turn, the plane's behavior becomes the key. Referring
Yeah.
to this page, we see a ground speed of 505.3 knots being maintained for a long duration. Why would a Boeing 777 fly for 7 more hours on such a steady heading rather than crashing in a jet?
Okay, so the crew, not quite. The crew wouldn't be incapacitated straight away at Agari there because it's a gradual decompression. So gradual decompression is going to take some time before the crew are hypoxic. So it's quite plausible it could have been 20 to 30 minutes before they're hypoxic and now um, unable to save themselves. But if you look here, so this is just my prediction when I was so this is not Malaysian data here. This is just me plotting points on the primary radar data, getting points to try and get an accurate sort of an estimate of the flight path. So you can see at the top there, ADS, ADS-B data. We know the aircraft was there at 17:20 and 34 seconds UTC. So that's the time in aviation. And that's just a standard 25-degree angle of bank turn back towards the nearest airport. Now you'll see on the east coast there, the nearest airport is Kota Bharu. So that would be the nearest airport. But at that particular time, Kota Bharu is actually closed for the night. So there's no runway lights. So there's
Oh,
no way
okay.
you can there's no way you could actually land there. So actually, the nearest suitable airport is Penang, which is over on the western side there of the Malay Peninsula. So,
Okay,
and
Penang,
when
yes. Yeah.
over there. So if you're going to land at Penang, you would actually go to the south of Penang and line up with the runway. Now, the captain is from Penang, so he's very familiar with it. So the nearest suitable airport is Penang. So they've basically turned back towards the nearest suitable airport. Now, with that turn back, when you actually look at the primary radar plot, it's not actually a straight line. So it's not actually in lateral navigation. It's still in either someone manually flying it or it's on autopilot in heading, which matches
Mhm.
the turn back there I just mentioned before. So that turn back was either manually or in heading mode, not in
Mhm.
lateral navigation. So in other words, why are you doing this? We tend to fly in lateral navigation. We just pick a point and go direct to away you go. The only way you do that is, or why you do that is if you've lost lateral navigation. In other words, for example, your left flight management computer has now gone kaput. Now, as soon as
Mhm.
that's gone kaput, you've got no other option but to manually fly and go in heading mode. Until you can get the right FMC back up and running, then you'll get uh, lateral navigation back available. So from that, we can see the aircraft's turned back in heading mode. And then
Mhm.
one other thing's going to happen when we get to the south of Penang. The first officer's phone connection, his actual phone connected at 17:52 and 27 seconds UTC. So
Mhm.
from that, we can get an estimated average ground speed. So the average ground speed there is 505. Um, so it's not actually a constant speed. The wind will change a little bit, but that's the average ground speed there. So we can work out how fast it's going. Now with that
Mhm.
first officer's phone connection, the first officer's phone was not on at Kuala Lumpur when he departed. So therefore,
Mhm.
the first officer has turned on his phone en route, something you might do if you've lost all your radios. Now, the only way that phone can connect to the cell phone tower in Penang is
Mhm.
if he is on the inside of the turn and near a window. So you can see the turn to the south of Penang is a very slight right turn. So because the aircraft's slightly turning to the right, it's sort of like a constant distance from the cell tower on the ground, and that would be
Mhm.
enough for the frequency to be stable for his cell phone to log on. So the first officer's turned on his phone, but the good thing of that is it gives you a position fix of where MH370 was, and it confirms that this flight path on primary radar is MH370 because that's the first officer's phone. Now, remember, the first officer sits on the right side of the aircraft, so
Mhm.
therefore the first officer's phone was turned on and most likely was in the front right cockpit. So in other words, the first officer is still in the front right side of the cockpit. Because if he's in the cabin and he's locked out in the door, then his phone's probably not going to connect because there's too much inside the cabin, there's too much obstacles in the way. So the most likely for
Mhm.
the phone connection is the first officer is sitting in the right-hand seat of the cockpit. Now, if we skip to the next slide, we'll look at we can work out again another position fix. So from Penang, for some reason now, the aircraft is now back in lateral navigation. So in other words, they've got the right FMC up and running. So someone's manually flicked the right FMC up and running. And now you're going in waypoint to waypoint. So you can see now it's tracking up to Avampi, Mika, and then towards Nilam. So that means the
Mhm.
lateral navigation is back up and running. So when you manually reset that FMC, what's going to happen to the flight ID? That flight ID is going to delete. It's going to go back to the startup situation. You'll only have the aircraft ID, no flight ID, and that ties in with what we saw with the SATCOM log, or what you're going to see with the SATCOM log at 1825. But however, we then have the last primary radar point of the Malaysian one at over there at 10 miles to the northwest of Mekar at
Mhm.
1822 and 12 seconds UTC. So again, we now have a position fix. So we can then estimate the average ground speed from the phone connection to the last primary radar point, and you get a ground speed of 504 knots. So therefore, when you put in the winds, you end
Mhm.
up with different altitudes and different speeds, and you basically end up with a one answer. The best fit is the aircraft had descended 1,000 feet from 35,000 down to 34. So it's
Mhm.
descended to 34,000 feet and is flying at Mach 0.84. So what does that mean? So when we fly eastbound, we fly at odd levels. So that'll be 35, 37, etc. So when I was going up towards Beijing, I was flying at 35. And when you fly
Mhm.
westbound, you fly at even levels. Yes, so now it's going at 34. So they've descended 1,000 feet. And why would you go at Mach 0.84? Well, Mach 0.84 is 84% speed of sound, which is the long-range cruise diversion speed of a Boeing 777. So in other words, the turn back has been done in heading. They've descended to a correct altitude. They've gone to the correct diversion speed. Then when they've got to the south of Penang, they've got the FMC up and running and gone into lateral navigation and flying at
Mhm.
Mach 0.84 up via these waypoints. Note that the last primary radar point there at Mekar is it
Mhm.
well within range of those three other radar sites. So Lok, Samawi, Sabang, and Phuket, but they're not available. Um, so that's not an instantaneous ground speed maintained all the way. That's just an average ground speed that I had there. It should be noted that the Malaysians said the aircraft was going faster than it possibly could. When you look at the report, the reason for that is they didn't actually use the warmer temperatures of the day. They just used the standard cold temperatures. And by doing that, to get the same true airspeed, they inflates the Mach number. So therefore, by using non the actual standard temperature of the day rather than the actual temperature of the day, they've made the impression that the aircraft was flying faster beyond its limits, which it hasn't. It's just gone at a standard divert speed.
But does
Um,
it seem normal to you for authorities inflating numbers like that?
Pardon?
Who are expo Does it feel normal to you for them saying that the plane was flying faster than what it should have been because they missed the temperature of the day to cal in their calculations? Does that seem normal to you?
Yeah, that's a question for the Malaysians. Like, why would you not use the actual temperature of the day? Because if you're just using, assuming that it's a normal standard day, then you're going to get errors in your results and it's going to lead to misinformation.
Okay.
Um,
Uh, okay. Uh, my next question is this one, bringing this slide back again in picture. And so you have identified a specific flight path towards Banda Aceh right here. You
yep.
have highlighted the Sultan Iskandar Muda Airport, WITT, as well. Uh, why is that airport so significant from a pilot's perspective during a land as soon as possible emergency compared to other regional options?
Yeah, it's not. So Banda Aceh does not appear as a land as soon as possible airport. But what you've got to do is you've got to put yourself in the pilot's seat. So you're
Mhm.
faced with all these complex failures. And now, whilst you're working through all these failures, like restoring systems, like getting the left bus back up and running from the right side, getting the right FMC up and running again, and just working through the mountain of checklists that you have to do. If you're now going so busy, and remember, both of these pilots are smokers, so they're more susceptible to hypoxia. Now, when you're diverting back to Penang without an active route, the cabin altitude warning would default to 15,000 feet because there's no active route rather than 10,000 feet. So by the time the altitude warning goes off at 15,000 feet, that could be equivalent to 20,000 feet for these two smoking pilots. That's assuming that they got the warning at all. And the other thing is one of the symptoms of hypoxia is you may be aware of the warning, but you don't have the mental capacity to then do something to correct yourself about it. So you're going to make strange decisions. So when you look at the fuel load, so we got a speed. When you look at the fuel load, so we had the last ACARS report at 1707 UTC, and it showed it had about 43,800 kilos of fuel on board. Now with that speed, you can work out the fuel flow rates. So I've done all that and did all graphs and worked out the fuel flow rates, and you've got to add 1.5% for the performance degradation allowance for that particular engines, all those engines. You find that the aircraft is actually too heavy to land at Penang. So you're going to have to, you're over your maximum landing weight to land at Penang. So you're going to have to do an overlanding weight checklist. You're going to have to do another thing. So there's, on top of all the other failures you've got, it's going to just compound more and more. And with that, with a complex failure, if you look at, for example, QF 32, Qantas QF 32, which had the uncontained engine failures in Singapore, it took them over an hour before they were even ready to land. So diversion back to Penang is only half an hour. You're probably not even ready to land. And then you get to the point where, well, hang on, they're hypoxic and they're making stupid decisions. So they could have just as the pilot could have put in a diversion to Banda Aceh because they thought that was the most logical thing at that particular time for someone with impaired mental capacity. And one thing you should note is if you follow this route, Banda Aceh would be the first time that the aircraft weight would be below the maximum landing weight. So to a hypoxic pilot suffering from hypoxia, a diversion to Banda Aceh may actually seem reasonable or logical at that particular time. And then it goes on who to say, well, maybe it's not the hypoxic pilots who have actually done this diversion to Banda Aceh. It could be one of the flight attendants. Now, this is where it gets a little bit interesting because let's say the pilots have done the diversion towards Penang and they started repowering buses and all that stuff, and they eventually pass out from hypoxia, and they've programmed diversion to Banda Aceh and they pass out from hypoxia. The flight attendants, they will probably come forward to the flight deck with their portable oxygen bottles and they'll find two pilots passed out from hypoxia. So what do you think they're going to do? They're going to try and revive those pilots. So the aircraft could be flying up the Malacca Strait with two dead pilots and the flight attendants trying to revive them. So how would they do that? They would grab the pilots' oxygen masks and try and put it on the pilots and put some positive pressure in there to try and get him breathing again. But that's not going to work because those masks are attached to those crew oxygen bottles, which have just exploded in the electronics bay. So if they're now empty, then you're not going to get those pilots back to consciousness. So now it could have been a flight attendant who then said, oh, what the hell do I do? Divert to Banda Aceh. Or it could have been an engineer. Now, remember, there was an engineer on board who was a passenger, and one of the flight attendants actually had a flight simulator at home. So any one of those people could have programmed a diversion to Banda Aceh. Now, once you've done the diversion to Banda Aceh with the autopilot on, they're portable oxygen bottles, which don't last very long. They're going to go empty, and eventually everyone's just going to pass out from hypoxia, and the aircraft's going to continue on autopilot up the Malacca Strait, going vamping Mikar, Nilam, Sanam, over the top of Banda Aceh, and it'll just continue south to the southern Indian Ocean. So, yeah, why go to Banda Aceh? Yeah, strange, but not for a hypoxic pilot or a flight attendant or a paxing engineer who doesn't really know what he's doing.
Wow. Okay. Okay, I want to share this Ocean Infinity search proposal that you made. I have a few questions on this. And is it fair to say that you think this was not a controlled ditching, but rather an uncontrolled high-speed crash impact, MH370?
Yes, when you look at all the debris and the data analysis, so the BFO's 15,000 feet per minute descent rate is pretty extreme. You wouldn't ditch like that. When you look at the fuel load, yeah, it's run out of fuel. And you look at all the damage of the debris from the nose, the tail, the vertical tail, the horizontal tail, inside the cabin, everywhere. Every part of the plane has been bound, the extremities, so therefore it's run out of fuel. So
Okay.
how would it get there? Yeah, as I said, it would have went over the top of Banda Aceh, and that's the
Mm-hmm.
beauty of the um, when you look at all the failures. One of the failures of the left system was the left auto throttle. So when you go back to um, up near where it logged on, so if someone had programmed a diversion to Banda Aceh,
Mm-hmm.
the aircraft automatically programs a descent point. You may have seen that on one of my previous slides. I'll actually probably,
Okay.
if you find that.
Let me know. Sure.
Um, so it might go back to that slide, and then we'll go back to this one. So you'll see here, top of descent point. Yeah, that last one you just had.
This one?
So no, there was the one that said top of descent point near the log on. Keep going, keep
Oh,
going, keep going, keep going, keep going. No, keep going, keep going, keep going.
this one.
There, no one there. Yeah, so
Go
with
ahead.
this one, so this is the thing. So if so this is a picture of the log on to the north of Banda Aceh here. So remember, it was going up Vampy, Mika, and towards Nilam. So I predicted that it went Nilam, Sanob, Banda
Mm-hmm.
Aceh. So once you've got the FMC back up and running and diverted to Banda Aceh, it'll automatically put in a top of descent point, which is very close to that primary radar point. So when you go back again, at that fuel flow or that speed that we worked out of Mach 0.84, 34,000 feet, there's at that particular fuel flow rate, there's no way the aircraft could maintain that for another 7 hours. So it actually has to slow down. There's just physically can't. There's not enough fuel on board to maintain flight for 7 hours. So it has to slow down to a more economical fuel flow. So once
Mm-hmm.
you've got a diversion to Banda Aceh in there, that you've got a top of descent point. So what's going to happen is the autopilot's going to go all the way along this route, and as soon as you get to the top of descent point, the auto throttles, which control the left and right engine, are going to
Mm-hmm.
try and slow down the aircraft to the descent speed. Now, the descent speed is a lot more economical fuel flows, and this will
Mm-hmm.
happen automatically even if everyone's passed out from hypoxia. However, the beauty of this is that to meet all the satellite arcs at this top of descent point, there is no left auto throttle. In other words, the left auto throttle or the left accelerator, so to speak, is inoperative on the left engine because of the failures to the left side. So the only way the aircraft can automatically slow down to the descent speed from Mach 0.84 is for the right engine to power all the way back. So what
Mm-hmm.
you'll end up with is the left engine still remaining at high thrust, high fuel flow, but the right engine is now all the way back towards idle. So what that's going to happen is because no one's programmed a descent, because they've all passed out, the aircraft's going to maintain 34,000 and it's going to slow to this econ descent speed. So now
Mm-hmm.
when it continues on at this slower speed, it can increase its endurance, but it still needs that last little bit. It needs the bleed air systems off. But if the bleed air systems are off, everyone's going to pass out from hypoxia. But by having the bleed air systems off, then the fuel flows have reduced enough. And now it's possible it can maintain flight for 7 hours. So therefore, from this last primary radar point, the aircraft has to slow down to descent speed and it has to
Mm-hmm.
have the bleed air systems off from Agari. In other words, everyone's going to be hypoxic. So now with this scenario, it meets all the arcs and all the BFOs and it ends up down there. So what's going to happen now is it's going to go at the reduced speed. It's going to go to Nilam, Sanob. It's going to go over the top of Banda Aceh. And because
Mm-hmm.
there's now no programmed route, it reverts to a heading mode. So it'll go to magnetic heading. So once it goes magnetic heading, it will just continue that south until fuel exhaustion. So yes, it passes. First of all, you'll get the call at 1840. So um, that call matches, and then it passes arc 2 on time, passes arc 3, arc 4, arc 5. And what then happens, because they got the differential thrust, the left engine's going to flame out of fuel for like 70 minutes prior to arc 7. And once
Mm-hmm.
the left engine flames out, the still everyone's still deceased. So the left engine's flamed out 70 minutes prior to arc 7 because of that differential thrust. The right engine's going to spool up or go increase to try and maintain that speed of that descent speed, but because it's so heavy at a high altitude, it just can't. And then it'll get to its what they call the stick shaker speed, slow speed, and the system will actually automatically pitch the nose down to maintain flying speed. So now, when you look at that, the aircraft is now slightly descending, hence the BFO for the second call matches. And now, because it's going even slower, it now doesn't overshoot Arc 6 and 7 and finally ends up crashing at that spot that I've predicted, which is still unsearched by Ocean Infinity. Hopefully that answers your question. Sorry to ramble on a
Yeah,
bit
no, no,
there.
of course. No, 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 please. The more details you are, the better it is for us to understand,
Yeah.
especially from your technical point of view. So I have two questions on this. So once again, uh, you have a 15,000 square kilometer 2024 proposed search area extending out 45 north miles from Semathor between latitudes 33 degrees south and 36 degrees south. My first question to you on this is, uh, as Ocean Infinity concludes its current phase of scanning in the southern Indian Ocean, what is the what is your assessment of the high probability zones they have targeted? Uh, and number two is, if they come up empty in this wider search, does it move the search closer to the Semathorc or further away, in your professional opinion?
Okay, good questions. So what we have here is this is the Ocean Infinity proposal graphic here. You can see the sort of like the orangey band, browny orangey band on
Right,
the
right.
outside of the arc, on the outside of
Oh,
the
this
arc.
one. Okay,
That's on the
yes.
inside of the arc. On the inside of the arc, and that's on the outside of the arc. So they've
Hmm.
they've searched outside the arc with no success. So they're covering the scenarios of a pilot, still alive to then glide it further and then crash outside the arc. Um, so my proposed area is actually that brown area on the inside of the arc. So between latitudes 33 and 36 south up to 45 nautical miles. The reason being is because if we go back to the scenario of diversion of Banda Aceh, it defaults to a heading mode. Now, once you go
Hmm.
to heading mode, you have to get, as it goes south, the magnetic variation is going to change, the wind's going to change, which is going to change the track over the ground. So if I have a 1 degree error in the actual magnetic heading over the top of Banda Aceh,
Hmm.
that after 2,400 nautical miles of flying, that could equate to a 40-mile error. So early on in 2016, I actually suggested 33 to 36 south out to 45 miles inside the seventh arc. But then COVID came along, and that gave me a lot of time to spend here in the office and to fine tune my pencil. And that's where I then fine tuned it down to that 25 nautical mile radius of 34.2 south, 93.2 east to try and
Hmm.
fine tune it. So why am I inside the arc? I reckon well, it's the only area left for a start, and my flight path is the simplest. So it's just basically divert to Banda Aceh, left systems fail, just let it go. That is so simple compared, and it still hasn't been searched. The simplest answer has not been searched. All these other ones rely on turns, climbs, descents. In other words, more assumptions and pilot interactions to get there. The reason I'm going inside the arc, because when you go back to log on one, way back up north of Banda Aceh, the those red bands, if to not overshoot them. So those BTO bands, I should say, they were never designed for the aircraft to be used this way. So in the communication logs, the aircraft will send a log on. It'll send a message from the electronics bay to the satellite data unit in the tail of the aircraft, towards the tail of the aircraft, and then up to the satellite. So you can work out on the timing just using the speed of light. There's a bias for the aircraft, and the residual bias would result in how far it is from the satellite. Hence, that's why you've got arcs 1, 2, 3, 4, 5, 6, and 7. So arcs 1 and 7 are actually initiated by the aircraft. So, and arcs 2 to 6 are just handshakes, just replies. So
Hmm.
arcs 1 and 7 are the ones which rely on the electronics bay being in a normal electronic state. So if that electronics bay has been damaged, then there is question marks over the integrity of the accuracy of these arcs for arcs 1 and 7. So when you go back to Banda Aceh, some people have predicted rather than overshooting, you'll see that rather than overshooting the arc 1, they predict the aircraft turns 90 degrees to the north, so it doesn't overshoot those arcs. Fair enough, but you're assuming that the arcs are actually accurate and the aircraft is still accurate. In my assumption is the aircraft just continued west,
Mm-hmm.
going to Nilam and Sanad, which then means that the arcs are actually too far east. There's an error. There's an actual unknown error, which is highly possible considering if the electronics bay is damaged, then the timing from the electronics bay to the aircraft's antenna is probably going to take longer than normal. Now, just remember that 100 microsecond error is going to equate to a 30-kilometer distance error. So if that aircraft's taking longer to send the message from its damaged electronics bay, then that's going to mean that if it's taking longer, then the arc should actually be closer. So the true position of arc 1 should actually be closer to the satellite. Hence, fast forward when you come to arc 7, because arc 1 was in error, arc 7 would probably be in error too, using that assumption, so that arc 7 should actually be closer. Now, arc 7 is an automatic log on, but in this scenario, it's because there's both engines have now flamed out. So now, once both engines have now flamed out, you've got the what they call the auxiliary power unit using residual fuel starting up and repowering the left main bus again and doing the log on. Or it could have been that an engine was repowering, but or tried to self-relight during the dive and hence repower the left main bus, and there goes the log on with still everyone deceased. But because now you've got the APU starting, there could actually be even more BTO bias in that log on. So in other words, the integrity of the seventh arc has a big question mark over it. And in this scenario with the damaged electronics bay, then yeah, it's very highly likely that arc 7 is in the wrong spot. It should actually be a lot closer to arc 6. Hence, that's why I said you should be going towards arc 6, because arc 6 is just a handshake and it's probably more reliable than arc 7. And so they should search there. And where it's still the only area left unsearched in the proposed search area.
But so a couple of questions. First is, I also asked this question to Jean-Luc Marchand. Has any authorities, ATSP or Malaysian authorities, ever contacted you or consulted you? Have you ever spoken to them regarding your proposed search area and this proposal?
Yeah, early on, I sent all the paperwork in and just went into the big black hole.
Oh, okay. Now, my follow-up question, the last question on this slide is, based on the physical debris found so far, what do those final moments look like to you compared to what is being searched for on this map?
Sorry, say that one again.
Based on the physical debris found so far, what do those final moments of the aircraft look like to you compared to what is being searched for on this map?
Yeah, well, if the aircraft's in a high-speed descent, then yeah, the aircraft probably broke up in flight or on impact with the water, unfortunately. So the debris field, yeah, it's going to be scattered. It's not going to be aircraft intact. It's going to be scattered. Now, the problem that I have with my data, with my predicted point, if you have a look on that map, it's right over the top of a trench. So I've called Rapari's Trench. That's going to be very difficult to try and find if it's in that trench. I just hope that the final point's out by a couple of miles and might be in a bit more easier searchable terrain within that 25-mile radius. But yeah, it's going to be hard for. Still a difficult task to find debris on the seabed at 4 or 5 kilometers depth.
Okay. I have a couple of other questions on the slides, and then we should be good to go. Now, seventh. Okay. There is much debate about the Inmarsat satellite pings, and you have suggested the data might be corrupt. Turning back to the technical logs, How does a physical electrical malfunction change the way a satellite tracks a plane's movement? And could that explain the offset in the search area?
Yeah, so I sort of explained it previously with the BTO bias there. So what you've got here is, this is again my prediction here. So top of descent, the last primary radar point. And so if you're going at that descent speed, then the aircraft would be at that little yellow dot there, 1825-27 log on near Nilham. So if you remember, the predicted program flight path would be Mika, Nilham, Sanob, Banda, Aceh. The aircraft doesn't actually fly directly over it. It does turn anticipation. So prior to getting Nilham, prior to Nilham there, the aircraft does a slightly left turn to join the Nilham Sanob track. So that's the orange line there. Now, the interesting thing with MH370 is back prior at 1803, when the aircraft was near Palau Perak, which is also known as Silver Island, out in the Malacca Straits, Malaysia actually sent a message to the aircraft, but the satellite system of the aircraft wasn't actually online. So if we have a look at, hopefully you can see this picture. I'm holding up MH370. I've put two little purple marks on top because the aircraft actually had a unique
Could
satellite
you move
system.
the plane a little bit up? I'm sorry. Yeah, now we can see.
Yeah,
Please go.
it had a unique system. So it actually had like a dual aperture high gain antenna. So that the high gain antenna is the antenna which communicates with the satellite. So it actually has, to put a little purple mark there, a left antenna and a right
Mhm.
antenna. So what it does is, if the satellite's on the left side of the aircraft, it uses the left antenna, and if the satellite's on the right side, it uses the right antenna. And I'll just switch between the two as it sees fit. So as the aircraft was flying up past Palau Perak at 1803, the aircraft is actually heading northwest. So with that in mind, with Inmarsat's Indian Ocean satellite, which sits over on the equator at 64 degrees east, it would mean that the satellite is on the left side of the aircraft. So in other words, the aircraft is trying to communicate with the left high gain antenna, but it wasn't online. So the aircraft could still be repowered at this stage. So remember, someone's repowered the left main bus, but it still may not be able to communicate because the left high gain antenna, again, another left system, is inoperative, and that's why it couldn't connect. So now fast forward, you come up to this position here at Nilham. As the aircraft now turns at Nilham, I've drawn in that little white line. You can see it almost goes at tangent to the orange flight path. So that white line is the direction of the satellite at that particular time. So what's going to happen, and what do you notice that at that particular point? It's at a tangent. So the aircraft is now turning left from Nilham towards Sanad. So what's now going to happen? It's now going to expose, at that exact time, it's going to expose its right antenna, right high gain antenna. And so the system will automatically, of the aircraft, will switch from the left, which is inoperative, to the right side high gain antenna and log on. Hence, everyone can still be deceased, and the aircraft just logs on there because it's now exposed the serviceable right high gain antenna. Now, when you look at those communication logs, that antenna, that communication was actually of poor signal. Why would it be a poor signal? Well, the geometry makes sense because the antenna is now having to almost transmit at 90 degrees along the fuselage over the nose of the aircraft. That is a very poor coverage section. Hence, that's why the reception of that first signal at 1825-27 is of poor quality. That BFO, well, yes, it's a startup signature. That doesn't actually match the startup signature. So it's almost like that BFO should have been overshooting by more, but it doesn't. It's almost correct. So that's strange in itself. It's almost like the aircraft's had time to log on, but it's now done a suspended start. In other words, that's what you would get if the left high gain antenna is failed. So everything in the satellite data and the timing matches the failure of a left high gain antenna and an operative right high gain antenna. So now if you continue on, the BFOs show that at 1828, the aircraft was turning left. Well, guess where the aircraft is at 1828? It's turning left. It's Sanob towards Banda Aceh. But as you can see, that red thick line is the 1828 arc. So
Yeah.
my prediction is that the aircraft was actually over at Sanob. In other words, there's an extra BTO error because the aircraft's over at Sanob, not on that red line. So the Arc 1 has a question mark over its validity, which then puts a question mark over Arc 7's validity. Hence, Arc 7 should be closer to Arc 6. You should be searching inside Arc 6, inside Arc 7 towards Arc 6. Yeah, so the BFO and the data all matches. Aircraft of the crew trying to get systems back up and running with a left high gain antenna failed, and they're just overwhelmed by hypoxia, and the aircraft just flew on until fuel exhaustion in the southern Indian Ocean.
Final question on the slide. We have gotten a lot of questions regarding this, and you would be the best person for us to ask. So, critics of the ghost flight scenario often argue there is no SDU switch in the cockpit to explain why the satellite unit went dark and then rebooted at 1825 UTC. However, it has been noted that the SDU is powered by the left AC bus. Referring to the timeline on this slide itself, could a pilot or a specific electrical failure use that bus as a de facto switch? And why would that power have been restored an hour later?
Yeah, well, that's actually an argument for the accident scenario. So if you were trying to not leave a digital footprint, you would turn off the left main AC bus, which depowers the SATCOM, or more to the point, the satellite data unit, and that would depower it. So therefore, you would not have any of these transmissions at all. So you wouldn't have ARCs 1, 2, 3, 4, 5, 6, and 7 at all, and you wouldn't have the two calls at all. So if you were trying to maintain, invisibility and not have a digital footprint, you would just turn it off and leave it off, which then goes back to the previous argument of, well, why go to the point of deleting the flight ID and then turning it back on to have no flight ID but still have the aircraft ID? You could have just left the satellite data unit off altogether and you wouldn't even have to worry about the flight ID as well. But if you look at from the perspective of an accident scenario, well, if the power to the left main, if there's a fault on the left main AC bus and the system just isolates that bus by itself to protect that system, the crew procedure is to restore power to that left main AC bus. And how would you do that? Well, there's many ways, but one of the ways is to repower it from the serviceable right main AC bus. You just flick a switch and repower the left from the right, and that's what the crew would do in any normal situation if they're trying to save the aircraft. Now, the BFO logon showed that the only way you can get that cold start overshoot is the left main AC bus has to be off for at least 22 minutes. So in other words, someone has to be alive for at least 22 minutes, and that's possible when you've got a gradual decompression at Garis, and someone has repowered it after 22 minutes, which is then sent power possibly from the right main to the left main, which then repowers the left satellite data unit. But of course, it can't log on without a serviceable left high gain antenna. So that needs to work as well. And that's not going to happen until you turn at Nilum there and turn towards the southwest. So now that the satellite is on the right side of the aircraft, and so now you're using the right high gain antenna, and hence it logs on. And as you continue south, you're just heading south. The satellite is always on the right side of the aircraft, and it just keeps responding. And that's why there was also at 1840 a call came from the ground to the satellite to the aircraft, a telephone call. It connected at 1840, so that's 15 minutes after the logon. But everyone is still deceased by this time. Why didn't they answer that call? Now that call got through this time at 1840, but no one answered. Well, if everyone's passed out, they're not going to answer a call. Same a bit further down at I think it was 2312, another call came in and that was unanswered. Well, again, if everyone's passed out from hypoxia, they're not going to answer a call. It's just going to go unanswered. So the restoration of the logon is actually more consistent with an accident scenario, and the lack of flight ID is accident scenarios. So I don't know why we spent nearly 12 years looking for a pilot hijack. It's just got too many more variables and assumptions where you should have just went with the basic simple answer. Someone diverted it, someone's programmed a diversion to an airport, as strange as that seems, but not to a hypoxic pilot, and just let it go. It matches everything. It matches fuel load, matches satellite data, matches the arcs. Yes, there's a question mark over arc 1 and 7, matches the BFOs, matches drift analysis, matches debris analysis, matches the barnacle analysis, and is still unsearched and is actually the only area still to be searched.
Wow. Wow. Oh, okay. Two questions before we wrap this up. I know we went pretty deep in this, but I think this was important uh, coming from your perspective. If we were to find the wreckage tomorrow, what is the one specific component you would want the ROVs to photograph first to prove or disprove the mechanical failure theory?
Well, the location, if they find it at 25 mile within the 25-mile radius, it's pretty logical that the aircraft has then flown over Banda Aceh to get there. That's highly likely then because it's the least assumption. But if you had to go down to photograph it, well, first of all, I'd like to see who was in the cockpit, how many people were in the cockpit, and the identity of those people. So it's possible you'd probably still see the captain and the FO, the first officer, still in the cockpit, and maybe even a flight attendant in there, as well. So I want to know how many people were in the flight deck, their identity, and the other big one would be I'd want to see pictures of the two 3,150 litre oxygen bottles which Malaysia topped up prior to departure to see if they've ruptured or imploded to see what sort of damage they have been caused.
Okay. Final question. If this latest search ends without a discovery, what does a permanent unknown mean for the families? And what does it say about aviation safety that a Boeing 777 can simply vanish in our modern world?
Well, aviation safety is still, or one of, or no, it probably is, the one of the safest modes of transport you can get. So on my day, I'm more likely to be involved in a car accident driving to and from work than actually in a flying accident. So statistically, it's still one of the safest. The Boeing 777, yeah, is still an amazing aircraft. The amount of backup systems and safety systems it has is amazing. However, no aircraft is ever going to be reach utopia. There's always accidents are going to happen, especially if a maintenance organization, for example, doesn't maintain their aircraft or oxygen bottles to the correct standard. Well, that's going to cause problems beyond the design certification of the 777. So as far as the 777, I have no problems getting on board a 777. So I'm not saying that. Again, I'm just hypothesizing it's probably the oxygen bottle. Time will tell when we get there. Um, but looking at all the evidence, as I said, the flight radar, the speeds, the fuel flows, the timing of the explosion, the timing of the log on, the BTO, the BFOs, the debris drift, the debris analysis, the barnacle analysis. It all points to a simple explanation is the oxygen bottle has actually ruptured in flight, which is unheard of and it's a rare event. It's unfortunate. However, I can definitely see, yep, it just looks like the crew have gone, yep, with all those problems, they've gone back to the nearest airport to Penang. They're starting to get hypoxic because they've missed the gradual decompression, unfortunately. And then for some dumb reason, someone's programmed a diversion to Banda Aceh and just let it go with all the less systems failures. And I can definitely see that those crew were probably working hard and valiantly trying to save the aircraft. So, and any crew in that situation would probably struggle too if that was the cause of the flight. They were going to be overwhelmed with so many failures. And if they've passed out, I could probably, I can also see a male or female flight attendant coming up trying to save the day, but finding two, pilots passed out from hypoxia, and then they're trying to reach for an oxygen mask and put it on the pilots, but it's unfortunate that the bottle's ruptured as those masks don't work. They're just going to pass out as well. Their portable oxygen passes out and it just continues on to fuel exhaustion. So yeah, and it's probably a bit disheartening too that if we had have had the a lot of the misinformation corrected, like uh, uh, like the speed and the way it turned, and also if we had all the primary radars, so if we had Phuket's, Lok Samawi's, and Sabang's primary radar data, it would have minimized the search area straight away. You would have found it pretty quickly. So that's a bit disconcerting about that one. But as lastly, it's just the only consoling aspect I can of a gradual decompression and hypoxia I can give the next of kin, to the wonderful people like Denisha Weeks and Grace Nathan, lost their mother and husband, etc. The only thing I can give them is that the if it's a gradual decompression led to hypoxia, then all the occupants have peacefully passed out, and they'd be totally probably even unaware that they've passed out, and that would have happened well before fuel exhaustion. So by the time that the aircraft got to fuel exhaustion 7 hours later, with them all passed out, they'd be totally unaware of the events that were happening, and they would be totally unaware, and they wouldn't experience any pain in those final moments when the aircraft ended its flight in the southern Indian Ocean.
Man, this is, I mean, uh, just like yourself, our heart goes out to the families of the loved ones who have lost, their members, family, colleagues, friends. And 12 years later, I hate to use the word closure, but some sense of peace of mind for them would be the best thing at least the officials can do. I know they are trying their best, and we don't want to uh, badmouth anyone here because this is once again a whole community that we're building here just to seek answers. Nobody knows what happened. We all have our own assumptions and own theories, and that is why we are a platform where we are neutral and we are inviting people who have credible voice, and let the audience decide for themselves. Uh, Captain Peter, your journey reminds us that while the ocean is vast, the law of physics and aviation are constant. Thank you for your technical dedication, your commitment to the truth of flight safety, and for joining us to share the story of the search that never stopped. To our audience, if this conversation moved you, please share this episode. By spreading the word, you ensure that this story and the 239 lives it represents is never forgotten. Our collective attention is what keeps the search for answers alive. Captain Peter Turner, thank you for being with us today.
Thank you, Sid. Thanks so much.
Thank you. Take care. Bye bye.